Foundation models for robotics, discussing a presentation by Sergey Levine he gave at a CVPR workshop actually this year. And there's two things I want to discuss here. One is the concept of foundation models for robotics, what that even means. In other words, why foundation model? And this goes back to the large language model conversation, and what's the difference between, let's say, large language models, transformer-based models, and foundation models. So I want to talk about this. And then second, actually, I also want to bring up a couple of works and mentions that support the thesis that there is transfer learning between navigation skills and manipulation skills. And this is really important for us here at Orange Capital Partners, because we have a large investment in Tesla, and the idea is that we have navigation skills and manipulation skills in a synergetic, learnable way. So in other words, the full self-driving of Tesla can help Optimus, and Optimus can help the full self-driving. This is not even a podcast. It's November 5th, 2024. This is Krim Dalko. For the day, the fund is up 4.5%. The market is up 1.2%. For the year, we're up 27.4%. The market's up 21.4%. We're outperforming by 6%. So this presentation by Sergey Levine is about a robotics foundation model. So what is a foundation model? A foundation model is a general model that is trained in a way that it can be applied to different downstream tasks. This is the key. So it can be, as the name says, it can be a foundation for further tasks to be either fine-tuned, trained on top of it, or just in one-shot learning used. So we could have a situation where, for example, in the presentation, Sergey talks about extreme cross embodiment, which is, by the way, all the presentations and papers are in the show notes. So I don't want to, boggle people down with details, with titles and things like that. So please check the show notes for all the links. Fundamentally, I think what's going on here is that we want to try to understand if a robot that picks up a fork, and another robot that cleans an apartment, and a third robot that drives, let's say like a cyber cab, if those three tasks learned separately can potentially be improved if they're learned in conjunction. This is the key. This is the question that this line of work is trying to solve. So there's, for example, Dhruv Shah, the PhD student of Sergey, who's now with DeepMind. His whole PhD is about that. Just to quote three questions of his PhD: how can we learn robust behavior from offline data sets of robots deployed in challenging environments? So this would be the first question in his PhD. Now, this in itself is more of an end-to-end learning type question, but then we go on. How can we make these behaviors generalized to challenging new environments, tasks, and robotic embodiments, and build a robotic foundation model, right? So can we have end-to-end learning of robots in specific tasks environment, and then potentially have one model applied to all of these tasks and learn from data sets from different separate tasks, and then have that model be deployed back in those tasks and realize, well, maybe the robots are better if they've been trained in a conjunction with other with other tasks. So again, if I train a robot to pick up a fork, and another robot to pick up stuff clutter on my floor, and a third to clean my apartment, and the fourth is my cyber cab, what if I have a model that is trained on all of these data sets, and then I apply these tasks with that model? Can I do better than with models that are dedicated just to those tasks? And the answer of Dhruv's work and the extreme cross embodiment paper that's also linked in the show notes is that yes, there is transfer learning. And I mean, this was the biggest takeaway from CVPR this year, in my opinion. It was the workshop on autonomous driving, where one of I think it was the DeepMind person, he told me that, and I guess he must have been inspired by Dhruv's work. who is now with Open of DeepMind, so a co-worker of that person, that there is, in cross embodiment, we have transfer learning. This is the key. And the question for us in Orange Capital Partners is always, well, how deep do we want to go, right? I mean, do we really want to understand the techniques? For example, in this case, we have a sort of a graph learning subroutine that tries to structure the visual embodiment. So in other words, the robot sees stuff, it's represented in some sort of point cloud, and then the position of the robot is, think of it like an edge, and then the vertex would be a transition function, and then you have different edges, or different positions and different transition functions that eventually get you to a goal. So this is kind of the approach. Again, I think we don't want to go too deep into the weeds here. It's time consuming, and for us, again, it's obviously a challenge, right? How deep do you want to go? Because you can't just dismiss it. You can't just say, well, we're not engineers, we don't care, because the learning, I mean, this is we're learning about learning, and what's interesting about it is that sometimes you go into the weeds, and then you get inspired by something, and you realize that maybe let's say you can make an investment somewhere, or not an investment somewhere else, or you understand, let's say, why Waymo is not so much of a threat to Tesla. You understand why the Chinese electric car makers probably don't have a lot of edge over Tesla. I guess I just want to conclude this presentation with a couple of observations, right? First, it's amazing that Berkeley and Stanford are working on this, and others, but this is, it's a bit close to home, and it's okay. I don't want to hurt other people's feelings, but this paper, the extreme cross-embodiment paper, is a joint work between Stanford, Berkeley, and I think DeepMind. So that's interesting, right? These people are working on these problems, I think, because we have an investment surge in robotics, and I think this has to be related to what Tesla's doing with Optimus, what others are doing. I don't think this is a coincidence. I think it's driven by Tesla, and potentially also a little bit by NVIDIA. There's a lot of money going into the space, and whenever there's a lot of money going into a space, people get excited, people get inspired, and so on and so forth. So I think that's one observation. Now, when it comes to the cross-embodiment, I think what they've achieved in the paper already, I mean, this is academic work which is already published, so this is not science fiction, is that we can have, and to paraphrase Sergey in his presentation, that you can have a model which is trained on different data, RTX. Okay, let me just quickly explain what happened. What Berkeley did, or Sergey and others did, they told people, listen, whatever you're doing in your robot lab, send me the data. And they got a lot of data from different labs. People that train robots how to pick up food, other people train robots how to clean, robots how to navigate, drones to fly, all kinds of robotic embodiments. The data was then cleaned and structured, and so a foundation model can be trained on that data. That's what they did. They stored the weights and sent those weights back to the people and said, just use the weights. Don't adapt, don't fine tune, just use those weights now. And the people use this new model, this foundation model, on the tasks that they were initially sending the data to Berkeley, right? So let's say if I was training my robot to pick up a fork, and I sent that data to Berkeley, they use that data with all the other data in the foundation model. Now I'm using the foundation model with the weights. I'm not doing anything else, and I'm doing the picking up task again. It does better. That's the amazing result here. And I think this opens up the avenue and the door, or whatever you want, whatever metaphor you like, of transfer learning and synergetic learning between a full self-driving car and an Optimus robot. This is the key here. There's some technical explanations for why that is happening, and fundamentally it's because manipulation tasks are really navigation tasks. They just have, and they have very similar goals, right? In a manipulation task, what you're doing is you first and foremost have to go from A to B, whether it's your arm or your finger, or you go as a body and then stretch out your arm, you're always navigating. But then, of course, fundamentally, in the end, you also want to contact, right? Which is different than in the pure navigation skill, where the car never wants to contact anything. It just wants to go from A to B. But most of the task is the same thing. I'm navigating. So I have a map problem and I have a search problem. The map problem is where am I and what's my environment? And the search problem or the transition function is how do I get from my position to another position, either the final position or like in the academic world, what people are doing is they're sort of subdividing it into sub-goals and then searching transition functions or developing transition functions for, okay, I'm here, how do I get there? How do I get there, until I get to the goal? And this is really exciting. For us, this is the most exciting thing, again, probably that we've learned this year. Hopefully we'll learn more at NeurIPS coming up. But right now, this is at the current stage of knowledge, this opens up the window for first the idea that we have a company like Tesla even doing what they're doing, which is Optimus and Cybercab. That's very important. And second, I think that also opens up some philosophical questions about learning. Okay, why is it that we have this transfer learning? And what is a navigation task anyway? And I think Dhruv in his PhD, he talks about the graph learning approach, and I think that's probably a good idea. By the way, there's also another whole conversation about the transformer architecture as a base for foundation models. The problem there is a little bit the inference situation, and I don't want to go too deep into that, but I just want to mention that the idea of a transformer is enticing because it's working with large language models. So why shouldn't we just substitute language with position and position data, for example, or position and action data, and then do the same thing, like predict the next action based on the position, which is the prompt, to use the analogy. Yes, this could work, and I think there's some work there too. ViNT is a model I've discussed several times before on this podcast. First time I encountered it was last year at Baylearn, and ever since they've been around at NeurIPS, and these people come, the idea of a visual navigation foundation model for robotics is floating around. People are working on it, and I think it's exciting. I believe it's probably enticing to think that the transformer architecture that worked for language probably is not going to be replicated one-on-one on robotics data, but the ideas, the fundamental concepts probably will work. So again, to summarize here, this is really important work by, I'm using Sergey Levine as the point figure here, but there's a lot of people around. There's, Dorza Sadik, Chelsea Finn, Stanford people, Dhruv Shah PhD at Berkeley now at DeepMind, and others. So I don't want to hurt anybody's feelings here, but just mention that this work, the idea of foundation models for robotics, the idea of transfer learning between different tasks, cross embodiments, and fundamentally the suggestion that we actually have a potential for emergent learning and emergent behavior and transfer learning and actually better performance if we can combine different data sets into one foundation model, train those, and then go from there, because that opens also the door for the bootstrapping. So once, imagine you have a model that can absorb all kinds of different data sets with different tasks, Now now the robots could potentially learn from other robots, right? You could start learning from other robots and they could bootstrap themselves. The more data we have about real world interaction, whether it's manipulation or navigation, the better the models get. So this is a generalization of the problem of real world interaction, which is subdivided into navigation and manipulation, but in the end it's interaction. And the more general the model is, the better it can learn and the better it can iterate. Thank you.